Let me talk about Artin's theorem. It's really part of the fundamental theorem of Galois theory. And the proof is quite subtle, and if you unpack the proof, you realize that we are using much of what we have developed so far. And this proof is the main non-trivial part of the proof of the fundamental theorem of Galois theory. So I want to at least sketch it. I have recorded on the right here some of the results that we have so far that we'll need. Let me just name them. Here is the primitive element theorem. And I need a corollary to primitive element theorem that we haven't done so far, so I should do that first. So I'll remind you, the primitive element theorem says that if you have a finite separable extension k over f, then there is some gamma in k, so that k is f adjoint gamma. So any finite separable extension can be obtained by adding a single element. The corollary says that you take some separable extension k over f. I'm not assuming that it's finite yet, but I'm assuming that there is a fixed number n such that when you take any element of k and add it to f, the degree of the extension fa over f is bounded by this fixed number n. Then the whole extension is actually finite and its degree is bounded by the same n. So if you can show that every a in k satisfies a polynomial with coefficients in f of degree less than or equal to n, then the whole extension degree is bounded by that number n. And why is this so? So you choose a in k such that the degree fa to f is as big as possible. I know that the degrees are anyway bounded by this fixed number, so I can choose an a such that this degree is as big as possible. My claim is that at this point, this thing is already equal to k. Let's argue by contradiction. Suppose it's not. What does that mean? That means that there is some b in k which is not in fa. Then if I add b to fa, I get this extension which is strictly bigger. But then, by primitive element theorem, this is again equal to f gamma for some gamma in k. Now here is the extension f gamma over f, whose degree is strictly bigger than the degree of fa over f, because you see this is strictly containing the other one. But that contradicts this maximality. And that's why this corollary is true. Okay. Now let's get to Artin's theorem. First I'll point out this lemma 2 on the right. It says that if you take a Galois extension k over f, and let's call the Galois group G, then the fixed field k upper G, meaning all elements of capital K that are fixed by every element of capital G, happens to be just the base field f. Artin's theorem is sort of a converse to this. It says that you start with a field k, any field, and let G be a finite subgroup of the automorphism group of k. This means the set of field isomorphisms from k to k. Okay. Then let's look at the fixed field k upper G. All elements of capital K that are fixed by every element of G. This is a subfield of capital K, so K becomes an extension of it. The conclusion of the theorem is that this extension is Galois, and its Galois group is the group G that you started with. So if you call the order of the group G n, then this extension has degree n. And I'm going to call K upper G by the name f. Let's see how this goes. The main part of the proof will be to prove that the extension is Galois. And we'll use this criteria C in lemma 1. It says that every element of K satisfies a polynomial in fx, which when you go to kx splits into distinct linear factors. That's how you check that a finite extension is Galois. Well, I don't even know at this point that the extension is finite, but we'll see. So take some a in k, and we want to show that its minimal polynomial in fx actually splits into distinct linear factors when I go to kx. But if you trust the result, you know what this minimal polynomial is going to look like. Lemma 3 told us how minimal polynomial of an element in a Galois extension looks like. It looks like this. Product x minus aj, where the product is over j equals 1 to r, and this a1, a2, ar are what are called the Galois conjugates of a, meaning you take a and hit it with all elements of the Galois group G. And we know that G in this case will turn out to be the Galois group in our theorem. So look at this orbit. Take A and apply every element of G, and you get a bunch of elements of K. A1, A2, AR. These are the distinct elements that you get, let's say. So this number R is the size of the orbit, which is less than or equal to the size of the group. And let's look at the polynomial that is there in lemma 3. So if we trust the result, we know that at the end of the day, this should turn out to be the minimal polynomial. The way it's written, it lives in kx because these aj's are picked from k. The first claim is that it actually lives in fx. And also, we should note that a1 I can assume is a because it's the orbit of a under a group. So x minus a is a factor of px. So if I know px is in fx, I'll know that a satisfies some polynomial in fx with coefficients in fx. Okay. Why is this true? Take some sigma in G. So this part of the proof is very much exactly like the proof of lemma 3 that we just did. Take some sigma in G and apply to P. This is product x minus sigma aj. But a1, a2, ar is orbit of A under the group G. So if you take the orbit and hit it with some group element again, then you get the same orbit back, possibly in some different order. So these elements are again A1, A2, AR, possibly with some different ordering. So that means sigma P and P are the same polynomial. So the coefficients of this polynomial, saying that sigma P equals P says that the coefficients of P are all fixed by G. So they're in K upper G. But K upper G is what F is. So that tells you Px is in Fx. That's the proof of claim 1. Before moving on, I want to make this observation which will be crucial. Just take stock what we have so far. What we have so far is that we have shown that every element, at this point we know that every element of K satisfies a polynomial of degree, this R is the degree of this polynomial, which is less than or equal to the size of the group N, fixed number. So if you add A to F, this extension degree is bounded by N. We know. Okay. So now that I know that every element satisfies some polynomial in Fx of degree less than or equal to N, we can look at the minimal polynomial. So that P sub A is the minimal polynomial. My claim is that P is P sub A. So P is the minimal polynomial. P of A is 0 because x minus A is a factor, you see. A equals A1. So the minimal polynomial divides any polynomial that A satisfies. So P sub A divides P. On the other hand, if you write P sub A out, these coefficients are in F. So if you take some, and this polynomial is also also has a as a root. It's minimal polynomial of a after all. So Cj to the j is 0. Now you take some sigma in G and apply sigma to both sides of this equation, then you get sigma Cj, sigma a to the j is 0. But what is sigma Cj? Cj's are in F, which is k upper G, meaning Cj's are fixed by every element of G. So in particular by sigma. So this is just Cj sigma a to the j, which is nothing but the polynomial p sub a evaluated at sigma a. Tells you that these sigma a's are all roots of p sub a. What are these sigma a's? They are these a1, a2, ar. These are the distinct sigma a's. So each aj is a root of p sub a. These are distinct roots. So each of these factors x minus aj divide p sub a. But these are distinct linear factors, so the product also divides. Well, that's your p. So pa divides p divides p sub a, so p equals p sub a. So this is the minimal polynomial. So that's the proof of claim 2, by the way. We are done with this. And we record that this is the minimal polynomial of A. But now you notice that this minimal polynomial has all distinct factors, so distinct roots. So not min poly of each A in K has distinct roots. Right here, A1, A2, AR. So that's the definition of separability, is separable. And now we bring in this observation, star. We have a separable extension, and for every element, the degree of the extension obtained by adding it is less than or equal to n. So by this corollary 5, so observation star and corollary 5 implies that the whole extension has degree less than or equal to n. So in particular, it's finite. Now that you know that this is a finite extension, you note that this here, this product, is a factorization of this minimal polynomial into distinct linear factors. Now, this is a factorization of the min poly p sub ax into distinct linear factors in kx. So this criteria C tells you that k over f is Galois. It just remains to check that the Galois group is G. Now this group G is certainly a subgroup of automorphisms of K which fixes F pointwise by definition of F, because F is K upper G. So G is certainly a subgroup of the Galois group. On the other hand, now that I know that the extension is a finite Galois extension, the size of the Galois group, again by this lemma 1 up there, is the same as the size of the extension, the degree of the extension, which we just saw is less than or equal to n by this corollary to primitive element theorem, and n is the size of the group G. So here you have a subgroup of a group whose size is as big as the size of the group. That tells you that they have to be equal. So the Galois group is G.